The very first part says state the Kirchhoff's first law. Okay, then we have a circuit. Before we read the question, the upcoming parts will try to understand the diagram. Figure 5.1 shows a circuit containing a thermistor. Now, what is a thermistor? This is a symbol for thermistor. So thermistor is type of a variable resistor in such a way that if the temperature increases, the resistance of the thermistor drops. So thermistor is a temperature controlled resistor. If the temperature increases, the resistance of the thermistor will decrease. Okay, let's start again. Figure 5. So for the thermistor, if the temperature increases, the resistance of the thermistor will be decreased, and the current flowing through the thermistor will be increased. This is what we know. So thermistor is a variable resistor. Its resistance is being changed, or resistance can be changed. It has a negative temperature coefficient. What do we mean by this? The same thing, that you increase the temperature, the resistance would be having a negative effect. So increasing the temperature would decrease the resistance. That's why we say that it has negative temperature coefficient. So what do we have for the first one? The first one says we need to sketch a graph. And for what we need to sketch a graph? We need to sketch a graph. And then what happens? Sketch a possible variation. Sketch a possible variation of the resistance of the thermistor when the temperature is changed from 0 to 100. So as you increase the temperature, the resistance of the thermistor decreases, and at 100 degrees Celsius, the resistance would be decreased significantly, and the graph looks something like this. So the graph will be having negative gradient throughout, and the graph between temperature and resistance, it is usually not a straight line, it is a curve that looks something like this, and it should not be touching this point over here, because the resistance would not be actually reduced to 0. Even at higher and higher temperature, the resistance decreases and decreases, but it's never reduced to 0. But where do we study the graph of resistance and temperature? Chapter number 1 of electricity. When you open up the notes, the first set of electricity, first chapter, current electricity, in that you have the section of the graphs. In that section you have this one, the graph of resistance with respect to temperature, or resistance against temperature. With reference to current in the cell, explain why current in the resistor R decreases with increasing temperature of the thermistor. So you're changing the temperature of the thermistor, but you have to answer what happens to the current in the other one resistor. Resistor R is the other one resistor, and that current decreases. So this is what happens. They're saying as you increase the temperature of this one, why the current in this resistor decreases in the previous one, in the upper one, in the resistor R, why current decreases? So the simplest answer is because if we increase the temperature, the resistance of the thermistor will be decreased, hence the current through the thermistor will be increased. So more of the current from the battery will now flow through the resistor and lesser current will now flow through the resistance. Yeah, we can also answer it like this. If the temperature of the thermistor is increased, the resistance of the thermistor is decreased. Yeah, but that'll be the same thing. So the total resistance of the circuit will be decreased. The total resistance of the circuit will be decreased. It means after this one, the total current in the circuit, the total current, and I'm referring to this one now, the total current in the circuit will be increased. The total current in the circuit will be increased. And if there is more total current in the circuit, there is more drop across the internal resistance. So more voltage will be dropped across this one, and these ones will now be getting lesser share of the voltage. So these components will now get less voltage. So we have to answer for this one. So I'll say the voltage across R will now be smaller. And if it has smaller voltage, lower voltage, but the same resistance, then current should be reduced. Now let us answer it properly. Increasing the temperature, the resistance of the thermistor decreases. So total current in circuit increases. More PD across internal resistance R, less terminal voltage or less voltage across resistance R. So the current in the resistance R was equal to the voltage across R divided by the resistance of R. So R is same, but this thing, the voltage across R has now been decreased. That's why the current will decrease. So voltage across R has been decreased. That's why the current through resistor R will be decreased. This is one way of answering. The other one is the answer in terms of the sharing of the current. The electromotive force of the cell is 1.5. Okay, they have given us the values also. So this electromotive force EMF is 1.5 volts. Out of that 1.5 volts, some of the voltage would be dropped across the internal resistance. How much we don't know. At least now we don't know. Internal resistance of the cell is 0.12. Okay, so this resistance is 0.12 ohm. Resistance R as resistor. Okay, everything is coming now. This one has resistance 6 ohms. At a particular temperature of the thermistor, the current in the thermistor is 0.2 amperes. Okay, So current through this one is 0.2 amperes. For this temperature of the thermistor, determine the current in the cell. Okay, we need to find the current in the cell. All right, so very interesting question. For 2 marks, we need to find the current in the cell. So once again, formally speaking, if we need to find the current through the battery or through the cell, we would be needing the EMF, means the total voltage and the total resistance. We do have this value, but we do not have the total resistance of the circuit because resistance of one of the component is missing. So that's why we cannot directly use the formula which would have given us the answer in 30 seconds probably. So let's try some other way. One of the formula that we have whenever we have internal resistance is E equals to EMF equals to terminal voltage minus IR plus IR. EMF equals to terminal voltage plus current of the battery times the internal resistance. We are supposed to find the value of I. If we have everything else in this expression, we can easily rearrange it and find the value of I. Do we have the EMF? Yes, we do. 1.5. Do we have the internal resistance? Yes, we do. 0.12. What about the current? Current is meant to be found out. The only thing that we do not have directly is this one, the voltage, the terminal voltage. Terminal voltage. What do we mean by this terminal voltage? Means out of that 1.5 volts, some of the voltage, a part of the voltage is dropped across this one. What is the leftover voltage? Is it 1.4, 1.3, 1.2? That is known as terminal voltage. How do we find it? So in order to find the terminal voltage, what we can do is the other one has resistance 0.12. Okay, the current through this one is all right. Do we have any other value? The resistance R has resistance 6 ohms. Okay, this one has resistance 6 ohms. All right, we can make use of this thing. So the same expression, this expression can also be written as E equals to capital V is also written as capital I, capital R plus the other one as it is. Okay, wait a minute. Resistor R has resistance 6 ohm, and so actually we are given with the current in the resistor R, not in the thermistor, you see. So at a particular temperature of the thermistor, the current in R is 0.20. Okay, so this one is 0.20, not over here. The current through this one is 0.20 amperes. Yeah, then we don't even need it. So what we can do is I can easily find the voltage across this one, which would be equal to the terminal voltage. So what is the voltage across this one? V equals to IR. What is I? 0.2. What is R? 6. So what do we get? 6 times 0.2 would be 1.2 volts. So means the terminal voltage is 1.2 volts. Terminal voltage is 1.2 volts. So the value of this one is 1.2 volts. So you can find the terminal voltage using this component, or you could have found the terminal voltage using the other one component. So which one do we use? The one for which we are given with the data. So EMF is 1.5. Terminal voltage means terminal voltage is 1.2 plus capital I as it is, because we need to find capital I, and small r is 0.12. Then I equals to 1.5 minus 1.2 divided by 0.12. And let's do it on the calculator. Point 3 divided by 0.12 is 0.18. 0.18 amperes. So the current, total current, wait a minute, the 0.18 was it? It's 0.3 and divided by 0.3 divided by 0.12. Let me check again. 0.3 divided by 0.12. 5 over 2. 2.5. Okay. 2.5. So the current in the thermistor, sorry, the current of the battery is 2.5 amperes. Now what do we mean by this? It means the total current from the battery was 2.5 amperes. Out of that 2.5 amperes, 0.2 amperes flow through the top. And how much would flow through the bottom? In parallel, the current is divided, so it would be 2.5 minus 0.2, which is 2.3. So the current through the thermistor is 2.3. So we might be needing it. That's why I have stated the current through the thermistor also. In the next part, we are supposed to find the resistance of the thermistor. So resistance of the thermistor is equal to the voltage across the thermistor divided by the current through the thermistor. That should be it. The voltage across the thermistor divided by the current through the thermistor. Now, what is the voltage across the thermistor? It should be the same as the voltage over here. Why? Because thermistor and the resistor are connected in parallel. So what was the voltage across this one? 1.2 volts. Then the voltage across thermistor should also be 1.2 volts. So 1.2 divided by what was the current flowing through the thermistor? 2.3 amperes. So 1.2 divided by 2.3, 0.52. 0.52 ohms. So what do we have in the circuit? In the circuit, I see pretty much the same circuit that we have. Battery with EMF 5.0 volts. Would there be 5.0 volts across this one and this one? The answer is no, because some of the voltage of that battery would be dissipated across the internal resistance. So some of the voltage potential difference of the battery would be across the internal resistance. So let's say that is 0.5. The leftover 4.5 volts would be across this one, 4.5 volts will be across this one, 4.5 volts across if there were a third one connected in parallel, 4.5 volts across if there were a fourth one also connected in parallel. But 4.5 was just an assumed value because we don't know what is the voltage dropped inside the internal resistance of the battery. And by the way, this one is this component is LDR, light dependent resistor. What is the effect? If you increase the intensity of light on the LDR, the resistance decreases. Just like you had thermistor. For thermistor, if you increase the temperature, resistance decreases. Okay, so let's move on, continue with this one. The graph of resistance and the intensity of light is given. Okay, fair enough. State the Kirchhoff first law. The sum of currents entering a junction is equal to the sum of currents leaving the junction. The intensity of light on Z is 130 watts per meter square. The current in the battery is 38 milliamperes. Show that the terminal potential difference of the battery is 4.8. Okay, terminal potential difference of the battery is 4.8. So when the intensity is 130, what is the resistance of Z? What is the resistance of LDR when the intensity is 130? We don't know, but we can find it through the graph. So 110, 120, 130, 140, 150. So we need to find at 130. 130 would be this line over here. Then I extend it over here. So 100, 110, 120, 130, 140, 150, 60, 70, 80. So this one would be 120. The resistance when the intensity is 130 watts per meter square. The resistance is 130 ohms. So we have the total current in the battery 38. So we have this value 38 into 10 raised power minus 3. We know the total current from the battery. So internal resistance is also given, and we need the current from the battery is also given, and we need to find the terminal voltage. So what if we use the formula so that the terminal potential difference of the battery is 4.8. Okay, the current in the battery is 38 milliampere. Okay, so this one we don't yeah, what we know is the current of the battery is 38 milliamperes. So 0.038 or 38 into 10 to the power minus 3. 0.038 is withdrawn by the battery, and 0.038 the same current must return back to the battery. Now what is the voltage across this one? The voltage across the small resistor is equal to the current through the small resistor times the resistance of the small resistors. V equals to IR. The simple formula, V equals to IR. Now the voltage across that one equals to the current through this one, which is same 0.038 times the resistance of this one, which is 4.7. Then we multiply these two, 0.038 multiplied by 4.7. I get 0.1786, or I can say 0.18. So the voltage across this one is 0.18. Voltage across this one is 0.18. It means out of 5 volts, 0.18 volts will be dissipated across the internal resistance, or 0.18 volts will be lost inside the internal resistance. The leftover would be the terminal voltage. So battery is labeled as 5 volts, but actually it will not be giving you 5 volts, because out of that 5 volts, 0.1 volts have been lost inside the internal resistance. So what is the leftover? Answer minus 5, ignoring the negative sign, 4.8. So total 5.0 minus 0.18 into SF is 4.8. Now it means across this branch you once again have 4.8 volts. Across this one you also have 4.8 volts. So 4.8 volts across this branch, 4.8 volts across this branch. This is the terminal voltage. Calculate the current I2 in Y. Okay, for 3 marks. So I'll raise these annotations for a moment. We need to find current in Y. Means we need to find the current through this one. So the situation is, out of that 0.038 amperes, part of the current would flow through this one and part of the current would flow through this one. How much of the current flows through Y, that we call I2, we don't know. That needs to be found out. We know the total current of the circuit. So what I can do is, if somehow I'm able to find the current through the upper one, this branch, I can subtract this current from 0.038. So I'll be getting the current I2. How much current flows through this one? Let's find out. So in order to find current through this one, through both of them, because they are connected in series, they must be having same current. I need the voltage across these two combined divided by the resistance of these two combined. The voltage across these two combined was 4.8. You see, the battery is giving 4.8 volts. 0.18 volts or 0.2 volts were dropped in the internal resistance, so leftover would be given to both of them collectively, divided by what is the total resistance. We found through the graph that when intensity was 130, the resistance was also 130. 120. Yeah, resistance was 120. We can see through the graph when the intensity is 130, the resistance is 120. So the resistance of Z is 120. So what is the total resistance? These two are connected in series. The total resistance would be 100 plus 120. That would be 220. Now let's write on the calculator. So I'll be getting 4.8 divided by 220, which is 0.0218. So the current through both of them, basically I1, is 0.0218 amperes. So the current I1 is 0.0218 amperes. So I2 would be equal to the total current, this one, minus the current that flows in the upper branch. So if I subtract these two, 0.038, I get 0.16. So 0.016 amperes. We'll at least complete this question. So I'll speed up. Calculate the power dissipated in Y. So power dissipated, we have plenty of formula. VI, we have I square R, then we have V square over R. So let's see which one is compatible. Power dissipated in Y. For Y, what do we have? We have the voltage. Yeah, but we don't have the resistance of Y, or do we? Yeah, I think first we'll need to find the resistance also. Or we can use P equals to VI. The first one should have been fine. So P equals to V, the voltage across this one, 4.5. Battery was, sorry, 4.8. Battery, once again, battery was rated at 5.0, but 0.2 volts are dropped, or 0.18 volts are dropped inside the internal resistance. So the leftover voltage 4.8 is across these two and across this one. So what is the voltage? 4.8. Why not 5? Because zero point 0.2 dropped in the internal resistance. Multiply. What is the current through Y? We just found out the current through Y was I2, which is 0.016. So 0.016, whatever the answer was, multiply by 4.8, I get 0.078. Zero point zero 7.8. The intensity of the light incident on R decreases. So intensity of light decreases. It means the resistance of the LDR will increase. So less current will flow through LDR. Explain what happens to the terminal potential difference of the battery. So the resistance of the LDR decreases, and the resistance of LDR, intensity of light at the LDR decreases. The intensity of light was decreased, hence the total resistance or the resistance of the LDR has increased, and therefore the total resistance of the circuit will also increase. Total resistance of the circuit increases. It means the total current withdrawn by the battery or the total current in the circuit will decrease. And if the total current in the circuit decreases, terminal potential difference will increase. Because if you have less current, then less voltage will be dropped in the internal resistance. Hence the terminal voltage will increase. This is exactly the other way around of the previous question. You see, I'll relate with the previous one. In this question, you were having, if the current in the circuit increases, then more voltage will be dropped inside the internal resistance. Hence, the terminal voltage was decreased. So if there is more current in the circuit, then terminal voltage decreases, and if there is less current in the circuit, then terminal voltage increases. So you can note down this one as an important note also. Reason: because if you have less current, then less PD across internal resistance. So less voltage is lost across internal resistance, and that's why you get more as the output. But if you have more current, then more PD, more voltage is dropped across the internal. So October, November 2025, paper 2-4. A student uses a circuit containing an ammeter, a voltmeter, and a cell to take measurements to determine the resistance of length of nichrome wire. Define the resistance. So you need to define resistance, not the unit of resistance. So resistance is potential difference per ampere. Not ampere, because ampere is the unit of current. Potential difference per unit current. So resistance is a physical quantity it must be defined in terms of resistance. But if the question were, for example, to define ohm, but for the resistance we have first one. Quantity is defined in terms of the quantity. Unit is defined in terms of the unit. Draw a circuit diagram to show how the components should be connected. Use the symbol for a resistor to represent the nichrome wire. Okay, what is the circuit again? Ammeter, voltmeter, and a cell to take measurements to determine the resistance of, okay, and the nichrome wire will be represented by a resistor. So we need a battery, symbol for a battery. You can also use a switch if we want. We have ammeter, then we have nichrome wire, which is represented by a resistor. And a voltmeter needs to be connected across the nichrome wire. If we need to measure the voltage of nichrome wire, then the voltmeter has to be connected across the nichrome wire. Okay, let's move on to the next one. The student also measures the length and the diameter of the wire. Figure 5.1 shows the measurements recorded for each quantity. Length is recorded in meters, the diameter is recorded in millimeters. Okay, the diameter is recorded in millimeters, and voltmeter is recorded in volts. Ammeter reading the current is recorded in amperes. Okay, show that the resistance of the wire is 5. R equals to V over I. What is the voltage? 1.38. This is the voltage. That is the uncertainty in the voltage. This is the current, and this one is the uncertainty in the current. So we might be needing to use the uncertainties in the following parts. 0.276. Okay, let's hit it on the calculator. But they are writing everything in 3SF, so we'll write it in 3SF. And by the way, why is the answer written in 3SF? Because the raw data, the entire raw data is in 3SF. We use these two values for resistance, by the way. The first one is 3SF, the second one is 3SF. So the answer should either be in 3SF, or in our syllabus we can add one more. So either the same or one more, but never less. Calculate to 3 significant figures the resistivity of the nichrome. Formula is this. Resistivity is rho, area times the resistance divided by the length. Make sure we insert the proper units. And by the way, area in terms of diameter is, if you could remember, area is pi d square over 4. So instead of area, I'm writing pi d square over 4. Everything else as it is. Or you can find the radius first and then use pi r square. In the next step, we insert the values in the formula. This whole thing divided by the length of the nichrome wire is 0.864. So I'll write this one exactly in the same way on the calculator. Okay, so I have a fraction first and another fraction, pi into d square, 0.496 into 10 raised power minus 3, square of it, divided by 4, pi d square over 4 into 5 divided by 0.864. So I get 1.1, 1, 2, 3, 4, 5, 6. 1.1 into 10 raised power minus 6, but we need to answer in 3SF, so 1.118, so 1.12. Into 10 raised power minus 6. There you can see the calculation also. 1.12 into 10 raised power 4 zeros, 5 zeros, and then 1. 10 raised power minus 6. The next part, we need to calculate the percentage uncertainty in resistivity. Okay, we need to find the percentage uncertainty in the resistivity. So the formula of resistivity was pi d square over 4 multiplied by r, and this whole thing divided by length. The percentage uncertainties of all the physical quantities will be added. So what do we have in the formula? Just ignore the constants. You don't need pi, you don't need 4. So all you need is d square, r, and length. So I need to find the percentage of d, but I'll double this one because it is d square. The percentage will be doubled. If it were d raised to the power 3, percentage would have been 3 times. If it were square root of d, percentage would have been 1 over 2 times. Plus, what's the other quantity? R. So percentage of r will be added. Plus length. So the percentage of length will be added. Whenever you have quantities being multiplied or divided, you add the percentages. So let us find the percentages. So the diameter would be second value divided by first value multiplied by 100, and you do not need the unit conversion for this one. Doesn't make a difference. Percentage would be same. 496 multiplied by 100. So this one is 0.403. What about the second one, which was resistance? Okay, so the resistance itself does not have any value in the table. Resistance was found through voltage and current. We divided the voltage and current. So it means instead of resistance, I'll find the percentage uncertainty of voltage and the percentage uncertainty of current, because the resistance was not given directly. The absolute uncertainty is resistance is not given. Resistance was never in the table in the first place. Okay, let us find for the voltage. This one would be 0.02 divided by 1.38. So 0.02 divided by 1.38 multiply by 100. 1.45. What about the current? Current would be 0.001 divided by 0.276 multiply by 100. How much? 0.36. What about the length? So length is 0.001 divided by 0.864 multiply by 100. We have 0.1115, or I can say 0.12. Only the diameter one will be doubled, because in the formula we had d square. So 0.403, 2 times 0.403 plus voltage is 1.45%, current is 0.36, length is 0.12. So what do we get? No resistance is the final percentage we are getting. So the percentage uncertainty you can either write in 1SF or 2SF. I'll write in 2SF 2.7%. So a little bit tricky, because in the question you have to find the percentage uncertainty of resistance separately, because the resistance was never given directly in the table. You found the resistance by dividing these two. Anyway, let's move on to the next one. Determine the absolute uncertainty of resistivity. So what is the value of resistivity? 1.12 into 10 raised power minus 6 plus minus 2.7%. Let us find what 2.7% of this answer is. So 2.7% means this thing, multiply by 1.12 into 10 raised power minus 6. I get 0.00. Okay. We need this answer in 1SF. Absolute uncertainty is always in 1SF. So 3 into 10 power minus 8. (1.12) into 10 raised power minus 6 plus minus 3 into 10 raised power minus 8. So you can write 3 into 10 raised power minus 8, because this one is in 1SF. But if the question is that write the principal value along with the absolute uncertainty, then you need to ensure that the exponents are same. So you write this one, for example, 1.12 into 10 raised power minus 6 plus minus if I write 30, that will be 10 raised power minus 7. Oh, sorry, if I write 0.3, that will be 10 raised power minus 7. If I write 0.03, that will be 10 raised power minus 6. because 0.03 into 10 power minus 6 is same as 3 into 10 power minus 8. We can even see this on the calculator. 0.03 into 10 raised power minus 6. You see, this is the same as 3 into 10 power minus 8. But this is the way we write. If they say write the final answer along with the uncertainty, but in this question we were supposed to simply write the absolute uncertainty. That's why we don't need to ensure the exponents are same. All right. A nichrome wire X of length 0.45 centimeter, 0.45 meters, cross section area this much. The resistance of the wire X is 1.1. The voltage EMF is 1.3 and negligible internal resistance. So in this case, we'll be getting all 1.3 volts as the terminal voltage or as the voltage across this wire. You'll be getting all 1.3 because there is no internal resistance, no voltage drop, so no tax on the amount. Current needs to be found out. Current equals to voltage divided by resistance, 1.3 divided by 1.1. I give 1.2, 1.18 aka 1.2 into SF. The number density of charge carriers, which are the electrons in nichrome, is this much, and it is with the unit meters per cubic meters, or m raised to the power minus 3. So the unit is perfectly all right. 8.5 into 10 raised power 28. Calculate the average drift speed. So I equals to N A E V. So if we rearrange for drift speed, by the way, this formula is there in the data sheet also. NAE. What is the current? 1.2 divided by what is the number density? 8.5 into 10 raised power 28. What is the cross section area of the nichrome wire? 4.7 into 10 raised power minus 7. E, also given on the data sheet, 1.6 into 10 raised power minus 19. So this one will be 1.2 at the top, 8.5 exponent 28 multiply 4.7 exponent minus 7 multiply 1.6 exponent minus 19, right in 2SF, 1.9 into 10 to the power minus 4. And the drift speed in meter per second is actually quite small. Calculate the resistivity of the nichrome wire. Okay, R equals to rho L over A. You see, same formula we have been using several times. So resistivity equals to R into A divided by the length. The resistance was how much? 1.1. Cross section area, if I could remember, 4.7 into 10 to the power minus 7 divided by the length was 0.45, I guess. Yeah, 0.45. 45 centimeters, but we use in meters. We open the calculator. 1.1 into 4.7 exponent minus 7 divided by 0.45. Into SF I get 1.1 into 10 to the power minus 6. Okay, theoretical one. What happens to the reading on the ammeter? So there must be a change in the circuit. What is the change? The wire X is identical to wire X. Wire Y is added to the circuit in parallel. The more the resistors in parallel, the less the overall resistance. We know this thing for sure. For example, if you have a single resistor with resistance 20, if you have two resistors with resistance 20 connected in parallel, then the total resistance would be 10. So the more the resistors in parallel, the less the overall resistance. So the total resistance decreases. As you can also write this thing, because when we add resistors in parallel, the total resistance decreases. So the current in the ammeter will increase. And voltage, by the way, will remain same. You have added two resistors in parallel, the voltage across both of them will be 1.5, equal to the EMF of the battery. 1.3. 1.3 across the first one, 1.3 across the second one, or you can say the voltage of the battery is also 1.3. Total resistance will decrease, current will increase. If, however, the resistors were connected in series, so this is the first wire and this is the second wire connected in series, in that case the total resistance would have been increased, hence the total current in the circuit would have been decreased for series. For parallel, it's exactly the opposite. The average drift speed of the charge carriers in X. So drift speed is related by this formula, I over NAE. The total current has been increased, so the average drift speed would also increase. Oh, wait a minute. Oh, okay, so it says, yeah, my bad. It says average speed of the charge carrier in X. Okay, so what happens to the current X? Current in the first wire will be same as the previous one. So current is same. The voltage, the drift speed, the small v represent drift speed, would also be same. So I in X is same. So drift speed V at X is same. So what I told initially about the currents was the current will increase. I said the total current will increase. So the same current will flow through the front. So think about it this way. Once you were having a single wire, this one was 1.3. How much current was flowing? Current was 4.7 into 10 to the power minus, no. Current was 1.2 amperes. So initially, through the wire X, 1.2 amperes were flowing. What happens when you connect wire X with another wire Y in parallel? So the first one still draws 1.2 amperes, but the second one, similar one, also draws 1.2 amperes, and that's why the total current through the battery would have been increased. That would have been 2.4. So when we said the total current increases, it means the current of the battery. But how much current flows through X? Same. How much current flows through Y? Same. And if you further want to clarify why current in X remains same, because the formula of current is V over R. Let's talk about X. Current X would be voltage of X divided by resistance of X. Is the voltage of X changed? No. You connect even 100 resistors in parallel, the voltage across all of them would be same. So it is exactly the same as in this case 1.3. So this is same, voltage is same. What about the resistance of the wire X? The resistance of the same wire does not change. It is the same wire, we have done nothing to the wire, so the resistance of the very same wire remains the same. Neither of the things change. So how would the current change? Current through one of the resistive wire is same, but the word electric here is would not make any difference. हमने सिर्फ उसी को डिफाइन करना है पोटेंशियल डिफरेंस को. So define electric potential difference across a component. It is the work done or the energy transferred to the component per unit charge. Okay, then we have part B. A circuit contains 4 resistors and a battery of electromotive force 8 volts with negligible internal resistance. When the variable resistor has resistance R, the current in the circuits are 0.030 amperes. I1 and I2 are shown. Okay. So the total current coming out of the battery is this much. Part of the current flows through this loop and part of the current flows through the second channel. Okay, so think about it. There's a traffic coming from the road and it is divided into, it splits into 2 roads, and these two, the entire traffic, they meet once again at this point. So once they return back, it is exactly the same, 0.030 amperes. Determine the charge passing through the battery in a time of 4 minutes. Charge passing through the battery. Q equals to I into T. What is the current flowing through the battery? 0.030 into 4 minutes means 4 into 60 seconds. So 0.030 into 6 4s are 24. We get, let me put it to normal setting, 7.2 coulombs. So current of 7.2 coulombs flows through the circuit. A charge of 7.2 coulombs passes through the battery in 4 minutes. Then we need to find the current I1. So I1 is the current that enters the lower street. Okay, street I'm just saying metaphorically. The current that enters the lower loop, or the current that flows through the lower loop. I1 or I2, which one was it? Let me check. Find the current I1. Yes. So I1 is the current that flows in this loop. The current in this one is I1. If we know the total voltage across these, we can easily find the current is I1. That would be equal to the voltage, combined voltage of these two resistors divided by the combined resistance of these two resistors. So current will be equal to I1 will be equal to the combined voltage of this pathway divided by the combined resistance. This is I1. So according to Ohm's law, I equals to V over R. But the question is, how many volts would be there across these ones collectively? How many volts would be given to these two resistors collectively? The answer is 8 volts. So 8 volts across the second branch and 8 volts across the first one, because these two branches are connected in parallel. So 8 volts across these two collectively and 8 volts across these two collectively. If there were a third branch, 8 volts across that one. If there were a fourth branch, 8 volts across them. And then what is the combined resistance of these two resistors? Since these two are connected in series, we can simply add them. 4, 5, 6, 3 and 4, 7, 6, 7, 0. 6, 7, okay. So the voltage is 8 divided by 670. I should say this way, 670. 8 divided by the answer. Let's see what we get. 8 divided by 670. 0.012 into SF. So 0.012 amperes flow through this one. Then we are supposed to find the current I2. Okay, so I can label this one. This one current was 0.012 amperes. The question would be, think about it. The question would be, if a total current of 0.30 amperes flows through the battery, the total current was 0.030 amperes. Out of that 0.03 amperes, 0.012 goes downward. What would be the current flowing through the upper branch? Should it not be the difference of these two? It should be. So 0.030 minus 0.012 amperes. In the next part, we are supposed to find the resistance R. We are supposed to find the resistance R. Okay, we need to find the resistance R. What is the resistance R anyway? The resistance R is this one. How much resistance is this? The answer is we don't know directly, but there are plenty of ways you can find this one. For example, forget about everything else. Just consider the middle branch. Nothing else, only the middle branch. Just consider this thing. If I write down the equation of current for this one, the equation of current was the total current entering the circuit, entering this branch, equals to the total voltage across these two divided by the total resistance of these two. Forget about everything. I'm only looking at this part in the middle, the first branch. I'm looking only at this one. This one over here. The total current entering in this one is equal to the total voltage across these two components divided by the total resistance of these two components. Now, what is the total current entering these two components? It is I2, and we found out the value of I2, which was 0.018. What about the total voltage across these two collectively? 8 volts divided by, what is the combined resistance of these two? We don't know, but we can write an expression. The combined resistance would be 210 plus R. And now you can clearly see we can rearrange the expression and we can find the value of R. So for example, it would be 210 plus R equals to 8 divided by 0.018. So 8 divided by 0.018 minus 210. 234, which in 2SF, since all the resistances are in 2SF, so I can write it as 230. Still, there are plenty of ways you could have solved this one. Another attempt would have been find the total resistance of the circuit, but that would just make it more complicated. This is probably the easiest method that I can think about it. Let's scroll down to the next part, which is a part C. The variable resistor in B is fitted with a scale so that its resistance can be accurately determined. Okay, all right. The resistor of resistance 240 is now replaced by a new resistor X of unknown resistance. A galvanometer is connected as shown, and the galvanometer reads, okay, with reference to the ratio of resistances, explain how the circuit can be used to determine the resistance X. All right. So with this one, when the galvanometer, so this is a variable resistance, so we keep changing this one until when the galvanometer reaches null position or null point. So when galvanometer reaches null point, means no current flows through the galvanometer, the ratio of these two resistances is equal to the ratio of these two resistances. Always. When galvanometer reaches null position, the ratio of these two resistances should be equal to the ratio of these two resistances. The ratio of the resistances on the left side will be equal to the ratio of the two resistors on the right side. And we can make an expression. So for example, I'll say 210 divided by 430 equals to this resistance R. How much? The resistance at which galvanometer shows 0. So you'll be getting a specific value of that resistance. The resistance at which the galvanometer reads 0 divided by the resistance X. So the value of R would be found, which would be equal to the point when galvanometer reads 0. And you can cross multiply, you can find the value of X. And the thing is, why is that so? There are two different approaches if you want to get into the basics or the principles behind this statement. then we have to say that at null condition, the potential difference at the point A and at the point B will be equal to 0. The potential difference at these 2 points will be 0. That's why no current flows through the circuit. And if the potential difference is 0, it means the ratio of these two resistors would also be 0. Or you can also say it this way, that the ratio of these two is equal to ratio of these two. You'll be getting the same answer. Here we have the first one. A nichrome wire has a length 150 centimeters, which I would like to write it as 0.15 meters. Cross section area is this one. So cross section area is 2.45 into 10 to the power minus 7 meters square, and the resistivity means rho. Calculate to 3 significant figures the resistance of the wire. So read out the formula, read it out aloud. R equals to rho L over A. Remember that R equals to rho L over A. So we need to find the resistance. So the resistivity, which is also given in proper units, ohm meter, times the length 0.15 divided by the cross section area, which is 2.45 into 10 raised to the power minus 7. Then we hit it on the calculator. 1.12 into, write exponent like this, 10 to the power minus 6 into 0.15 divided by 2.45 exponent minus 7. So let's see what we get. 0.6, 0.857. Okay, 0.857 means 0.86. Wait, what? That's too low. 0.86. Our resistivity was 1.12 into 10 to the power minus 6. Let me check the data. Yeah, come on, boy. Syntax error. Just for one bracket. Oh, sorry, my bad. The nichrome wire has resistance 150. Okay, 150 centimeters. So 1.5 meter. My bad. So we get 6.857, which is 6.86 in 3SF. So a nichrome wire has a length 150, means 1.5 meter. You can simply divide it by 100. Cross section area is given, resistivity is given. You write down the formula of resistance, insert the values in the formula, find out the answer, write the answer in 3SF. That should be it. Must write down the formula that gives you C1 compensation mark. Even if the working ends up to be wrong, you should still be securing the first mark, compensation mark. The nichrome wire forms part of a potentiometer circuit. Okay. The circuit is used to determine, this is what we use the potentiometer to measure the potential or the EMF of an unknown battery without drawing the current in the circuit. So galvanometer is in a null method to find the null point 60 centimeter from the left and 64 centimeter given on the diagram also. Explain what is meant by the null point. The null point is Okay, sorry, not the null point. Describe what is meant by null method. So the method in which the galvanometer reading is or becomes zero. The reading of the galvanometer becomes zero. Calculate the EMF of the cell X. Very important question and a standard question of galvanometer. So this is a textbook example of galvanometer. Potentiometer. Whenever you get a question of potentiometer, this kind of variation is very common. Calculate the EMF of the cell X. How do we do? If this thing is in null state, it means no current flows through this one. That implies that the voltage across these 2 points is equal to the EMF. So I'm going to call it V2, for example. Then V2 will be equal to EMF of the cell X. So if galvanometer is at null condition, the current I equals to 0, then the voltage V2 will be equal to EMF of the cell X. The question is, how do we find the voltage V2? That's it. Whatever the voltage V2 is, that will be equal to the EMF of the cell X. So we are doing the method of cross multiplication. We know length volts on one side and centimeters on one side. So we know 1.2 volts for 150 centimeter. How many volts for 64 centimeter? Then you cross multiply. You multiply these two. 64 times 1.2. Let me on the calculator. 64 times 1.2 divided by 150. So this thing is getting only 0.512 volts, slightly less than half, 0.512 volts across this one. And it means the volts across the cell X would also be same. Why? Because no current is there in the galvanometer. This is a condition for the potentiometer. So whatever volts you get at the top would be same as the EMF of the battery in this case. So EMF of the cell X is also 0.512 volts. Or you can write it as 0.51 if you want to write in 2SF. Now this one is really difficult question to explain and to answer. We'll do it anyway, but this is the kind of question which requires extended concept. Initially, there was no voltage drop inside the internal resistance, but now the EMF of 1.2 is replaced by a new cell which has internal resistance also. So internal resistance is not negligible. Still explain the effect, if any, on the internal resistance of the new cell on the position of the null point. So if you have a cell which has internal resistance also, so 1.2 cell, this one was having no internal resistance, but now you have a cell which is of same EMF, but this cell has internal resistance also. So the cell now looks something like this. Okay, so this is the new cell now, the cell with the internal resistance. So what is the situation? If there is internal resistance, so out of that 1.2 volts, 150 centimeter, the nichrome wire, the full length of the nichrome wire will not be getting 1.2 volts, because part of the voltage would be dropped inside the internal resistance. So suppose 0.2 volts are dropped inside. So how many volts would be there in total? 1.0 volts. So now the length 150 is getting 1 volts. The length 150 is getting 1 volts. Okay, so just an assumed value uh, for comparison. So let's say 0.2 volts are dropped at the internal resistance. So the length 150 centimeter will now be getting not 1.2 volts, only 1 volts, because a small percentage is dropped inside the battery itself. Then what should be the length if what should be the length if the voltage is 512, 0.512? Let's cross multiply once again. So 150 multiply by 0.512 means at a length of 76.8 meters centimeters. So which means the null point will now be shifted slightly to the right side. How much was that? 76.8. So the null point will be shifted to the right side. The number 76.8 is just a reference value. It could be 74, it could be 75, but it would be necessarily greater than 64. That's for sure. It would be greater than 64, depending on how much of the voltage is dropped inside the internal resistance of the battery. So the voltage across the wire decreases, so the null point will move to the right side. A cylindrical copper wire of length 0.24 meters as shown in figure. The current in the wire is 0.85. The resistance of the wire is 3.3 milliohms. The total number of charge carriers is 2.6 into 10 to the power 22. The resistivity is given. Potential difference needs to be found out in the first part, probably the easiest one. Potential difference V equals to IR. V equals to IR. I represents the current 0.85 times the resistance, which is 3.3. 3.3. But this one is 3.3 milliohms. Point 0.85 into 3.3 10 power minus 3. So I get 0.0028. Or in 2SF, you can also write it this one in scientific form, 2.8 into 10 power minus 3. Show that the cross section area of the wire is this much. Okay, so you need to find the area. So we can easily use the formula of resistance in terms of area. R equals to rho L over A. Then you can swap R and A. So the formula would be rho L divided by R. Rho represents the resistivity. Resistivity is given already. So resistivity is 1.8 into 10 to the power minus 8. The length of the copper wire through which the current is flowing 0.24. Divided by the resistance of the copper wire is 3.3 into 10 raised to the power minus 3. Let's do it on the calculator. 1.8 into 0.24 and the exponent is 0.8 minus 8. 3.3 exponent is minus 3. So in 2SF we get 1.3 into 10 raised to the power minus 6. Show that the number density of the charge carriers in the wire is this much. So number density is represented by small m. The formula is number of charge carriers per unit volume. This is the formula of number density of charge carriers. Do we have the number of charges? Yes, we do. 2.6 into 10 to the power 22. 2.6 or 2? Yeah, 2.6 into 10 to the power 22. Do we have the volume directly? No, but we know for a cylinder the volume equals to the base area times the length. So base area of this cylindrical wire is cross section area, you can say base area, and the length was 0.24. Then let's do it on the calculator. Exponent 20, 2.6 exponent 22, 1.3 exponent minus 6 times 0.24. We get 3.8 into 10 to the power minus 28 into SF. Then we have the next one. Calculate the average drift speed of the charge carrier. V equals to I over NAE. Formula is given in the data sheet also. Current was 0.85 or what? Yeah, 0.85. Divided by number density of charge carriers as appeared on the calculator. 8.3 into 10 to the power 28. Cross section area was 1.3. The value of E is 1.6 into 10 to the power minus 19. Let's do this one on the calculator. Once again, 0.85, 8.3 exponent 28 multiply by 1.3 exponent minus x, multiply 1.6 exponent minus 19. The drift speed in 2SF 4.9 into 10 power minus 5. So 4.9 into 10 raised power minus 5. So done with all the mathematical questions. Then we have 6 mark theoretical questions. So theoretical questions for 6 marks. This one is a very standard question, should not be tricky at all. The radius R1 at the end of the wire Q is same as the radius of the wire P. The radius R2 is less than the radius R1. The radius R1 at the end of the wire X is the same as the radius of the wire P. Radius R2 is less than R1. Okay, a different copper wire Q has the same volume as of the wire P but non-uniform radius. Okay, so this is a wire Q. And what about the wire P? Okay, this one was a wire P. So I'll draw wire P also. And so this is a wire P and this is a wire Q. The wire P has uniform cross-sectional area. The wire Q has non-uniform cross-sectional area. The radius R1 at the end of the wire Q is the same as the radius of the RP. So the radius of the wire P was also R1, but for the wire Q, the radius at the end X is R1, but on the other side the radius is smaller. So here explain how the resistance of the wire Q compares with the resistance of the wire X. Okay. So resistance equals to rho into L over A. The two wires are made up of same material, which is copper. So the resistance would simply be independent of resistivity. It would be proportional to length and area, length and cross section area. So the wire which is longer and thinner, yes, will be having more resistance. The wire which is longer and thinner will be having more resistance. So if you have the more length and less cross section area, the resistance would be more. So we need to find out which wire has smaller cross sectional area. If we talk about the cross section area, the cross section area of the wire Q is smaller than that of wire P, because if I draw it on scale, it said wire P has the same as this one. Yeah, so this is technically, this is wire P. This side is same for wire P. Yes, that's better now. So this is the radius of wire P. And wire P has the same has a uniform cross-sectional area. The cross-sectional area of the wire P does not change, but the cross-sectional area of wire Q decreases and decreases. So we can say on average, the cross-sectional area of the wire P is greater than that of the wire Q. The average cross-section area of wire P is greater than wire Q, greater than that of wire Q. So if if wire P has greater cross-sectional area, it must be having less resistance. So the resistance of the wire P should be less than the resistance of Q. But what about the length? You see, the resistance also depends on length. So which of these two is longer? The answer is this one. The wire Q is longer because the wire Q has smaller cross-sectional area on average, but the volume is same. So volume equals to area times length. Now this is the tricky part. Volume equals to area times length. If something has smaller cross-section area on average, wire Q has smaller cross-section area, but it has the same volume, then how come you have the same volume? If one of the values being decreased, how can the answer of V be the same? It is only possible if the length increases in the same proportion. So wire Q is thinner and longer. So it is thinner and longer, so its resistance would be greater. So resistance of Q is greater than the resistance of the wire P. Resistance of the wire Q is greater than the resistance of the wire P. Okay, the last part, sketch the variation of the average drift speed of the charge carrier from end X of the wire. So from end X to the other side. So from a thicker side to a thinner one. The drift speed would be increased, and the drift speed is proportional to the square of radius or the square of diameter. So the graph would be something like this. Because drift speed is proportional to the square of radius. As you move from end X towards the end Y, the radius decreases. My bad, is inversely proportional to square of radius. So as you move from end X towards the end Y, the radius decreases, hence the drift speed would increase. And why do we not start from 0? Because even at the end X, charge carriers have a certain drift speed. If you start from 0, it means at the end X there was no drift speed, which is not possible. but that one would be minimum. That drift speed would be minimum. As you move along the conductor towards the thinner and thinner side, the drift speed would increase by a factor of square. And once again, how do we know the drift speed is inversely proportional to radius? By this method, n into a into e. If everything else remains constant, we can say drift speed is inversely proportional to area, but area can then also be written as pi r square. If pi is also a constant, then we can say drift speed is inversely proportional to the square of the radius.